far. This is true. I don't really know the students like class that well, so to me, it looks like ordinary students at the moment.
But there's so many more girls.
I know you.
Yes. But
Oh, the density of girls in physics, I don't know. Okay, so let's talk about Newton's third law. I talked about this last time, and I seem to have indicated that there was an error in my notes, and that is not true. I mean, there are errors in the notes, but not what I said. So first of all, what Newton's third law says that when bodies interact, forces come in pairs. All right. So just to set up some notation for our discussion, if F sub BA is the force of B on A, all right, and if force sub AB is the force of A on B, all right, so think about different bodies, putting forces on other bodies, right? Just thinking about pair of bodies A and B. Newton's third law says that those two come in a pair in the sense that FBA is equal to minus FAB, right? For every action, there's an equal and opposite reaction. Here's a precise mathematical statement of that, all right? So, a silly example, just to get us started. If you had, now this, you have to, this picture doesn't even quite do it justice, right? Because really, I'm neglecting the normal force and neglecting the force of gravity. Perhaps a better picture of this would be Mr. Top Hat and his mass are somehow like in the vacuum in space, and he's pushing on this box with a rod, all right? At that point of contact then, I'm telling you that Mr. Top Hat's putting a force F sub naught. So that's the force of A on B. Okay, what does Newton's third law say? It says, well, if that's the case, then there's another force that has to be there. It has to be a counter force of the force of B on A. All right, so the force of B on A has to be minus F naught. Taking, taking this direction. So basically, I'm saying this direction is positive, this direction is negative. We're in the one-dimensional case, so I can get away with not writing vectors here. But oh, now I'm writing vectors. Oh man. All of a sudden, I'm not in space anymore. Where am I now? What did I do? Yeah, I put it on Earth. Well, that's so boring. If you want to be off Earth, just set this stuff all to 0. Then you're in space. Start with that. Anyway, my point here is just that this stuff is vertical anyway. If you're on Earth, suppose you're on Earth for a second, this stuff cancels out. The normal force and gravity cancels out. So we can focus on the horizontal, which is what I was trying to do. And horizontally, the mass of A times the acceleration of the A body, which in this case, Mr. Top Hat, it would be equal to minus F naught I hat. Because, again, the contact forces of the box acting on Mr. Top Hat goes the opposite direction. In contrast, the mass of the box has a force of F naught on it, right? So there's two separate Newton's equations we can look at, and what happens here? So you can, horizontally, we can solve, and we have the acceleration of the box, rather Mr. Top Hat is to the left, all right? And the acceleration of the box is to the right. And they're not the same accelerations either, are they? So just draw a picture over here. I mean, one question people always ask, right? Is if every force, if every action has an equal and opposite reaction, then why does anything ever move? I mean, that seems like a fair enough question, right? Because forces always come in pairs. If the force pairs always cancel out, we learned that when the sum of the forces is 0, the acceleration is 0, right? So how is it that you can have action is equal to reaction and still have motion? Yeah.
Forces are applied to different objects.
That's exactly the point. Yes, the forces are applied to different objects. That's the trick. So here, basically, the net force horizontally is this guy, right? On this, on the other hand, the net force horizontally is that guy. So the acceleration of the A body is equal to ma over F naught, and there's minus here, which means it goes to the left. Whereas the acceleration for the B body is F naught over mv. And as you can see, unless the mass of Mr. Top Hat and the mass of the box are equal, these will be different accelerations, right? So either you need an extendable pull, or this is just over a moment that we're talking about, right? All right, so that's an example. Now this example I thought was wrong last time. Oh man. Yeah, we've been through this before. I wonder if I still got that open. Yay, my laziness works. Aha! Procrastination for the win. I should have shut this down like sometime since last class. I just leave stuff open, maybe get it up. Yeah.
Did you mean to write negative m sub a over f naught, or am I just
Yeah, the units here are somewhat questionable. Here we have a kilogram divided by a kilogram meter per second squared. We have an acceleration of second squared per second squared of a meter. That's a very strange unit for acceleration. There's a simple answer, which is I forgot to write this. Sorry. Yes. Thank you. Indeed. I blame women. Oh man. If it's a perfect world, I wouldn't sin. I have a perfect mind and a perfect body. I wouldn't make this mistake. Why are we living in a fallen world? Wasn't adequate. I mean, I'm just saying. He was there. Didn't say anything. I don't know. Interpretations vary on this point. Just kidding. Okay, mostly. So, for this, here's another very popular example, which I misinterpreted last time. So, okay, suppose you have two boxes side to side. We're going to ignore friction for the moment. And the question is, what's the net force on each box? What's the acceleration of the system? And also, we'd like to find the force of contact between the boxes. In other words, find the force that box 1 pushes on box 2, given that I'm pushing on box 1 with a force of F naught. Right, so you can imagine Mr. Top Hat over there, or if you prefer, you could, I don't know, maybe there's a dragon blowing fire on it. It exerts a force of F naught on the first box. I don't know, however you want to produce that force. It's up to you. So, on M1, I have M1A. What are the forces on this box? Well, I told you there's force F naught on it, right? There's also this contact force, the force of M2 pushing back on M1. So that's F21 on my labeling. All right? So there's Newton's second law for box 1. M1A is equal to F naught plus F21. Taking the right direction is positive. Oops. Oh.
Where's that from?
Yeah.
Actually, M1A is force naught minus
I'm annoyed. Sorry. I'm pushing this way.
F21 is negative.
Let's try this again.
F21 is negative.
I thought it was fine, but now I see there's a sign error, which I have somehow canceled out with another sign error. Maybe it's not wrong, but I can't see how to make it right at the moment, so let's put it away. Work it out. All right, so
The force comes back there.
there's perhaps an easier notation to do this problem in. Okay, so same problem. You start from scratch here. Here's your M1, and here's our M2. Okay, so I'm saying I'm pushing on M1 with a force of F naught, all right? And then I've got a contact force. So I'll show you the other notation we can use, which is just use C for the contact force. So C is to the left, right? I mean, this second box pushes on the right, the left box this direction, right? That's the reaction force from the second box. Clearly, the reaction force from the second box does not point that way, right? You don't push on the box and then the box like pulls you that way. That would be great. We all agree. And then M2, oh man, I fluttered it up. M2 though, what's the, stupid. Why is M2 in the way itself? Right? I'll draw it again down here. Oh well, poor planning on my part. What is the, on M2, what forces do we have here? we just have the contact force, right? I'm ignoring the vertical for the moment. So horizontally, we just have the contact force. Right? The given force F naught does not push directly on mass 2. The only thing pushing on mass 2 is mass 1. Now, I just use C for both. I'm using C to indicate the magnitude of the contact force, right? I'm going to put the signs in to indicate the direction by hand. I think that way I won't get confused, and I'll be happy. Well, as happy as we can be in a room with 10 too many people. So M1A. Oh, do they have the same acceleration? Well, I mean, they're stuck together. So the acceleration is just the second derivative of the position. So if they share the position, which is linked, the position's just shifted by a translation, right? And then if you differentiate the translation, like the additional piece goes away. They have the same velocity, it's clear. If they have the same velocity, they have the same acceleration. So yeah, they share the same acceleration because they're stuck together. So M1A is F naught minus C, is what I'd like to say. M2A is what? Just C, right? So you know, those are Newton's second laws in this case, where the reason I have C and minus C again is by the third law. Sorry for wasting your time for the last 5 minutes. I should have just told you that. Admittedly, the notation I was sharing with you, 1, 2 versus 2, 1, it's useful in a more general context, and we'll come back to that notation as we derive something more general later in the class, so don't feel too bad about waste of time. I'm just joking, it's not very soon. Now, so I can add these equations, right? And that will tell me what? Yeah. Well, I'm assuming the acceleration is the same. So it better still be the same, that's true. So what happens? The C's cancel, right? And you're just left with F naught. So what do we find? The acceleration of this pair of masses together is equal to F naught divided by M1 plus M2. About 30% of you, maybe, something like that, would just instinctively know that that's what the acceleration should be. I don't know. It's just like, and I see some nodding, but and I see this on the test because I have students who don't understand Newton's law, right? But they can still figure out the acceleration on this. Is that because they kind of know, when I say they don't understand Newton's law, I mean they don't understand Newton's law as it applies to the masses separately. There's a large class of students who can solve this problem, find the acceleration, but would not be able to tell me what the contact force is. Because you're not thinking of it in terms of a contact force, right? You're just thinking of it in this way. You're like, well, this is the same as just having one big mass, M1 plus M2, right? And the net force on that big mass is F naught. So the acceleration is F naught divided by the total mass, right? And you're not wrong, right? But I've derived that here. I've showed you that the internal forces of the system cancel out when you think about the aggregate motion. Is there a question? Comment? Maybe I shouldn't take comments. I don't know. What's the contact force? Contact force is what? C? Right. I think the laziest way to do it is M2 times A, right? So I just, that's F naught M2 divided by M1 plus M2. Just to kind of balance, I mean, to think about your intuition, see if this answer makes sense to us. What happens if the masses are equal? What's that?
You get F naught over the mass of that mass.
Right.
Which is F naught.
What if M1 is equal to M2? What does the contact force break down to? F naught what? Yeah, divided by 2. If the masses are equal, then the contact force is half the applied force. And if M1 is much larger than M2, the contact force is pretty small, right? See, if if this number is really big, M1 is really big compared to M2, then the contact force is really, really small. So for example, maybe, I don't know, maybe you've got like a big, or a car or something, right? And then you've got a what? A cat? Okay, very good. Yes, and then you've got a cat standing on the other side of the car, right? You push a car, most of your force is going to go into, pushing on the what? Pushing on the car, and then the contact force of the car and the cat is pretty small. Intuitively, that makes sense, right? Most of your force is just for pushing the cat. Now turn the situation around. Put the cat first, put the car second. Then the contact force is very, very large, right? So, in fact, almost all of the contact force is essentially equal to F naught. M2 is much, much bigger than M1. Contact force is essentially F naught. And then in between those two extremes, you have some fraction of it. Okay, but anyway, that's pretty much the standard third law question. For tests, just to make you suffer, I like to add a third box. And then ask you, what's the contact force here do? Right? But it's just more of the same. You have 3 equations rather than 2. We can work that out some other day. So I wanted to tell you guys a little bit about friction today. See if I can find it. See, hopefully I can get this to work again. Yep.
This may be a stupid question.
Take quickly.
Would it complicate things if there was a difference between, say, 2 points pushing on each other or 2 surfaces pushing on each other? Is that complicated or is it exactly the same?
Right. Your question is a valid one. I mean, I think if I strike to the heart of your question, you're basically asking me, I've got some macroscopic body, right? And I'm telling you things like, I push on the body with a force F naught, like this, for some angle, for example, like that's in the previous lecture, right? You're like, does it matter? Is there any difference if I was to say push here, or if I was to push here, or if I was to push here? What if I pushed over here? What if I pushed here? Does it make a difference? I think physically speaking, you guys know in your heart, if you search your heart, you know it's true. These are different. Right? You know full well that if the force is big enough, and this is like a wooden block, if you push on it here, the thing's going to roll over. Right? Whereas if you push on it over here, it's not going to roll over. It's just going to kind of slide. Right? And pushing it in different places gives you different kinds of possibility. Like, it may or may not be possible the thing rolls over, depending on where you push it, right? Those kinds of distinctions we don't address in this part of the course. That's chapter 11 on equilibrium. In fact, we skipped that chapter. So while your question is good, it's above our pay grade. So, all right. Now, if mechanical engineering starts offering a course on statics, I think that would be right up their alley.
Next semester.
Oh, there you go. So, but anyway, to answer your question, to solve such problems, all you do is say that the sum of if you're looking for equilibrium, you say the sum of the forces on the thing is 0, but also the sum of the torques on the thing is 0, but we don't know what torque is yet, so I don't know what to talk about. So as far as we're concerned, I mean, in some sense, what I'm telling you is, one interpretation of what I'm telling you is that push is a pull. I mean, because on the one hand, I can tell you that I'm pushing on the box with a force F naught, right? But I'm saying it's just the same as if I was to pull on the box with a force F naught. I mean, pragmatically speaking, for our problem-solving purposes, we don't make a distinction. Oh. Friction. So the sort of friction we talk about in here is kind of boring, but it's manageable. There's basically 2 kinds we're interested in. 3 kinds we're interested in. 2 mostly, though. The third one is we have this question of terminal velocities that we'll get to in the later class. I'm not talking about that today, except that I just talked about it. But anyway, ignoring that. You either have static forces of friction or you have kinetic forces of friction. So to give you an illustration of this, here you go. Static. The box, I'm putting force on this box, it's not moving, as you can see, right? And if I push hard enough, it starts moving, right? Now the box, the lecturant is still pushing back on me, there's still a drag force, right? But it's actually less of a pushing back. It pushes back on me less when it's moving, right? You've experienced this. If you have a really heavy box, if you can get it start to move, it's easier to push it. Whereas right up to the point that it starts moving, there's like a larger force pushing back. This is because the static force of friction is typically larger than the kinetic force of friction. So here's the way it works. Case one, if it's static, the static force of friction can be all the way from like, if I just do like this, static force of friction that the lecturant's pushed back on me is about 0. Right? And I can push on it harder and harder. Ooh, it's gonna really hurt my fingers. Right? Sorry. I can't even get to it. I'm pushing on my finger harder and harder. It's still not moving. Ow. I should break blood vessels in my finger. It's not a good idea. My point is, the static force of friction is adjustable. It can be adjusted anywhere from 0 up to this critical value of mu sub s, which is some coefficient that describes the force of friction between the two interfaces. In this case, whatever that lecturn's made of in the floor. There's some sliders on it, I don't know. But this is like the maximum value of the static force of friction. Static force of friction mathematically is a kind of complicated thing. It could be a lot of different things. There's a whole range of values it can take on. That's just the nature of the beast. We have to deal with it now.
Is mu normal force, is that when it will start moving, or the hardest you can push without it moving?
That's the hardest you can, that's the breaking point right there. When you get to that, if you get just a little bit past that, it'll move. These things are all approximate. I mean, these are approximate descriptions of motion. I mean, where is friction coming from? It's coming from this sort of microscopic interface of the wood and whatever else you're pushing into whatever two things you're pushing past each other. Well, if you look at a subatomic, if you look at not subatomic, if you look at atomic scale, right? There's these molecules, and it's like a mountain range, right? And then the other one's like a mountain range of just it's not smooth, right? If you look far enough, close enough, you'll see that even smooth surfaces are quite jagged. And friction is coming in part from those two jagged things sort of rubbing up, against each other. I think that's a lie. It's actually because the electric field of the molecules are pushing the other electric field of molecules in such a way that it creates a force in order to move it. But it happens that force is just proportional to the weight of the object, which is kind of awesome. So yeah, it's really, really complicated. One mountain range being sort of shoved past another, yet it just amounts to what kind of material you have, because I guess the shape of those mountains is somehow characteristic of the material. We will not derive that. So, N is the magnitude of the normal force. I've been using F sub N for that this semester. Because as I told you, using N for a force is a somewhat questionable practice, given that N is a Newton. All right, kinetic. Kinetic is easier. Kinetic force of friction is what it is. So it doesn't matter how fast I move it. That's a lie. We're ignoring that. But for our purposes, the kinetic force of friction doesn't matter if I'm moving it a little slowly, faster. It's definitely smaller when I move it faster. Whatever difference there is in kinetic forces of friction, we ignore those because everybody else does it, and that makes it okay. So for the purposes of not killing introductory physics students, we assume the force of, it's reasonable approximation for many motions that the kinetic force of friction is essentially just proportional to the mu times the normal force, yeah.
Wouldn't it feel easier simply because the lectern is gathering momentum? So it's fighting some of the friction force for you, but the friction force isn't changing, roughly.
Right, I can't process all that. I have math I can solve. But perception of force versus velocity versus acceleration, this I don't have. I'm sorry, I personally don't. Not my ninja way. You guys should jump all over me. I just said just a second ago that the static force of friction was proportional to the weight. That is incorrect. That is so incorrect. I have been making a point of showing you that the normal force is not equal to the weight in many examples. So I should say, it's the normal force, it's proportional to the normal force, the force of friction, yeah.
I don't know if you've already answered this, but it says that the normal force of like kinetic force is typically smaller than the maximal static friction force. Is there a time that it could be bigger? Or is that just like universally accepted that it's always going to be smaller?
Say again,
You said like in the bottom there it says F kinetic is typically smaller than the maximal static friction. Is it always smaller? Or?
that's an experimentally determined fact, yeah. As far as I know, I mean, there may be some exotic material which is designed precisely to be opposite that. Maybe those, I think it might be that the oblique is an example of that, possibly, this non-Newtonian fluid, that if you move slowly through it, you can move with relatively little resistance, but if you try to move your hand fast, it stops on you. But that would be kind of an example of that, but that's motion through a liquid. It's not a body sliding along another one, so I'm just making an analogy. Apparently, you make that stuff with cornstarch. I don't know, my wife used to do this for some K-12 teacher training thing. Okay, so here's some typical values. Steel on steel, static coefficient 0.7, kinetic coefficient 0.6. This is kind of your answer to your question also. Teflon on Teflon, 0.04 versus 0.0. I don't know.
Does one lose a 9?
Yeah, that's a good question. I don't know. If only there were some way in this age of the internet to find out for sure what the coefficient of static friction is on Teflon. See, when I was in school, I actually had to suffer through finding this stuff in a book. You guys can just Google it. But be careful with WebAssign. WebAssign doesn't care what Google says. WebAssign cares what perhaps is in the back of your book or what it said in the problem.
Usually it's the problem.
Yeah, usually what's in the problem, which may not be reality. So you should always think of WebAssign problems as possibly being from some sort of like alternate reality. In terms of not using accepted values, possibility. That doesn't seem right. 0.0. Wrote this.
I think somebody's been editing sevens.
Man, I think something happened there.
Was it 1.0?
No.
4.0?
No. Yeah, that's one thing we should notice. We never get to 1 in any of these. Like 1 is a hypothetical maximum. Like if you had a force of friction larger than, if the mu was larger than 1, that would be like force of friction, some sort of like force multiplier. It's taking gravity and somehow creating a lot. I mean, I don't know. Maybe that would be tape. Perhaps an adhesive might. I don't know. But here's an important one. Rubber on a wet road, 0.3, whereas the kinetic, 0.25. That's why you don't want to, and it's true on dry too, you don't want to spin your tires, right? Because when your tires aren't spinning, you're in the static case, because the rubber is just laying down on the road as it turns. I know it looks like it's not static, right? But actually the surface of the tire and the road, they're in static. They're not moving with respect to each other. When your tire starts spinning, that means that the actual point which the tire is hitting the road, with respect to the road, those are not statically there. So anyway, there's more to that also, but here's an example. We should look at an example. Suppose a box rests on a plane, all right, and we push with force F naught at angle theta naught. We worked that before, right? Without friction, a couple days ago, remember? Now I'm adding friction. And I'm telling you that the coefficient of static friction is 0.1, all right? Then what is the minimum theta for the box to stay put? So if theta is 0, what happens? Just for example, what would happen if theta is equal to 0? Right, you have F naught like this, right? You have, what's your normal force? You have normal force like this. You have the force of gravity down, right? Where's your force of friction? Now think about this, guys. It's common sense. Does friction point towards the motion or opposite the motion? What's that? Yeah, opposite the motion, right? Nobody's like, I was driving down the highway, all of a sudden I hit this patch of really sticky pavement, and my car just got thrown ahead. No, I mean, it slows you down, right? Friction slows you down. So now, but you're like, this is a static case, there's no motion, so what does that mean? It's against the direction of potential motion. So the potential motion is to the right, correct? So that means the force of friction should be, I heard some of you say, to the left, like this, right? So now we have what? We have 0 is equal to F, the normal force, minus mg. I'm looking at the theta equal to 0 case, which is easier on the board here. That's the horizontal, right? Oh, I'm an idiot. Horizontal? Is this the horizontal part? No, this is the vertical forces, right? Vertical. And then MA, we have what? MA is equal to F naught minus the force of friction, right? But the force of friction is mu sub s times the normal force. What's the normal force? In this case, it's the weight. In this very simple case, it is in fact the weight. So we have F naught minus 0.1 times mg. So if I don't want that, if I want, and if it's in the static case, what's the acceleration, by the way? What? What's the acceleration if it were in static case? We're not moving.
0.
Yeah, the acceleration 0. So the question is, can you even solve this equation? I mean, I wrote 0.1 here, right? But that's the maximum. That's the maximum force of friction that's available. Yeah.
So are we assuming, for the purpose of solving this, that theta is equal to 0?
Yeah, I'm just to get us started. I'll come back to the arbitrary theta on the projector in a second. So with my F naught? Where's F naught? I guess I need to know what F naught is, huh?
Well, better the math sense.
Yeah. So I guess the answer is it depends whether or not, I mean, let's see here. Take an example. Suppose F naught was the weight, right? Kind of a ridiculous example. So just for an example, suppose, let me make it a little bit more interesting. Suppose F naught was equal to the half the weight, so 0.5 mg. Right? If F naught is 0.5 mg, this is definitely not going to be 0, right? However, what happens is you raise the angle. What happens is you push on the box at a higher angle. What happens? Suppose F naught was still equal to 0.5 mg for the sake of our discussion at the moment. Yeah, the normal force starts to increase, which makes the force of friction bigger, right? But it's also, the other thing is, the horizontal force, the horizontal component of the force is also reduced, right? Eventually, we get to the case where the angle's 90 degrees, right? When you're at 90 degrees, it's definitely not going anywhere, for sure, right? So let's look at my derivation here in the general case. So say, okay, well, what would the situation be? I have MA. What are the forces at play? You got normal force, which I have foolishly written n vector. As I was telling you, we would do better to write f sub n. We have the force of friction, which is going to be opposite the potential motion, right? we have the force of gravity, which is down, and then the pushing force, which I'm allowing to go at an angle. And I've written it as a pulling force here because it's easier to picture that way. Right? This is the what? The free body diagram, right? And then I just look at the, the components of this equation in the x and the y direction. So in the y direction, you have the acceleration due to y, normal force goes up, gravity goes down. This is the component of the pushing, or if you like to think of it as pulling force vertically, right? That's just so that was absent over here because I was looking at theta equal to 0, sine of 0, 0. Now, of course, this should be 0, right? Because if the box slides on the plane, it doesn't accelerate with respect to the plane, so that should be 0. This, on the other hand, we've got the part of the force which is horizontal from trigonometry, right? Cosine theta is this side. And then minus mu sub s times the normal force. What's the normal force now? Like you guys were just telling me, it's not just the weight anymore, right? It's the weight plus this thing. All right, so if we want equilibrium, we want both of these accelerations to be 0, right? So I have to try to solve both of these at once. As I was telling you, the vertical gives me that the normal force is equal to 1. Sorry, it's like, what happened to my energy? Oh, man. No way.
You're solving the n ax equals n cosine.
Oh, am I? Oh, good. Yeah, no wonder I'm confused. All right. So for some reason, I solved the x equation first because I can. Now the y equation, on the other hand, if I solve for n, it's more exciting. mg plus f sine theta. Now, why did I solve both for n? I'm interested in what here? I'm actually interested in theta. I don't really care what the normal force is. So if I solve both equations for the normal force, then that removes it. Right? Elimination by the solution. Okay, then I have this. What can I do? Algebra. So I subtract sine theta the other side, I divide by this f naught, and that gives me this handy-dandy relation. The weight of the box divided by f naught is equal to 1 over mu sub s cosine theta minus sine theta. That is, so I've derived this equation under the assumption, right, that the force of friction is the largest it can possibly be. So intuitively speaking, that must mean that that's going to give me that minimum angle above 0 where it works. Does that make sense? Now, solving that equation is a bear, right? But you can do it for specific numbers. It wouldn't be pleasant, but you can do it. Yes. Can't do it. Oh, special case theta equals 0. But, you know. All right, here's a general discussion I should have here. Here's another way of picturing both cases at once. Your force of friction, what's possible? So static case, you can go from 0, right, all the way up to this maximum value, mu sub s times normal force, right? But then when the pushing force gets past that value, whatever it is, then the force of friction drops back down to this kinetic case. It's just this constant mu sub k times n, and that's the nature of friction. I mean, that's it. For example, if I had a box that had a static coefficient of 0.5 and a kinetic coefficient of 0.2 for a given surface, and the box just barely started moving when a force of 100 newtons was applied horizontally, I could ask, what's the acceleration if we continue to apply f naught as it slides? What does this mean? The box just barely starts moving with 100 newtons. What does that tell you? This transition from static to motion, where does it happen? For what magical force? Is it's not magical, it's just special.
Mu static.
Yeah. So we should be able to set mu static times the normal force equal to what? 100 newtons. Now, to be, sorry, this is how I used to solve things when I was a student, but now I force myself to think properly. Mass times acceleration is equal to F naught minus the force of friction, right? But that's the horizontal, right? Vertical is what? 0 is equal to the normal force minus mg, right? So therefore, the normal force is equal to mg in this case, because we're just looking at a horizontal force. We don't have the complications of theta I was just talking about. So, and just before it starts moving, what's the acceleration? 0, right? 0 is equal to F naught minus, and then not just any force of friction, but the maximum possible static force of friction, which was 0.5 times what? Times the normal force, right? But we know that the normal force is in fact mg. So what this tells me then is that 0 is equal to 100 newtons minus 0.5. Did I tell you the mass? I did not, did I? We can figure that out now. So mass times gravity. What's gravity? 9.8 meters per second squared, right? So you can solve this for mass. What do we get?
Kilograms.
24.1 kilograms?
20.41.
20.41. That's interesting. So what was my actual question, though? Explore box. What we're trying to find here. What is the acceleration if we continue to apply the force F naught as it slides? Aha! So now I know what? I know the mass. Right? Is that the question? Ah, put that there. Right, so what am I doing here? Well, I agree with this. I think I took a slightly different route in my solution up here. For some reason, I thought it was for me to find the mass this time, so I did. Here I'm working a little bit sneakier. Oh, I found the weight in my previous solution. See, that's the thing. You could either go with finding the mass, or you could go with finding the weight, right? These are two different ways you could solve this problem.
Wouldn't it be the normal force, not the weight? I guess
Well,
let's go through.
in this particular example, the normal force is the weight, right? I'm going to stick with my mass solution, though. Okay, so kinetic case, what do we have? We have MA is equal to what? The pushing force, which is 100 newtons, right? Minus the force of friction, which is u sub k, times the normal force, right? I mean, which is the weight, as it turns out. Now, so let's see here. I was trying to figure out what the acceleration was, right? So the acceleration then should be 100 newtons minus mu sub k, which we're given is 0.2. Right? The mass, which we just figured out was, well, see, this is what's kind of silly about solving for the mass, right? Is I'm just going to multiply it by g pretty soon. And oh well, it's 20.41 kilograms. And you can see how we're undoing what we just did, right? Mathematically. And then I have to divide all of that by 20.41 kilograms, but I mean, it's okay if you want to go with the way it is in the notes or the way it is here anyway, it's fine. Okay, so what do we got? Is that 40? So minus 40 newtons. divided by 20.41 kilograms. So I've got what, 60 kilogram meters per second squared divided by 20.41 kilogram meters per second squared. So what is that? That's about, I can tell from the exuberance of the whole, we're about done. Approximately 3 meters per second squared, right? Obviously that's not quite right. We're about 0.3 Gs. Now, anyway, we will, of course, work more examples of friction and stuff. You know, this friction, this case-wise nature of the static friction, it does make the problems trickier than what we've done so far. We need a day or two more thinking about this. You guys got some questions about your homework if you get stuck on all that. For those people who are C-files and have just come here to try to find out what evil it is that is universal physics, my message to you would be, become one with algebra. Become one with trigonometry. These two things you must know. Cold. Calculus will help you, but algebra and trigonometry are by far the thing people are too weak to do.
Thanks, guys.